So let's start the second part of this morning about chemistry with the lecture of Professor Sarathy, who is a professor of chemical engineering, not mechanical engineering, from KAUST. And we'll talk about net carbon-free fuel chemistry. And you, when you're ready.
Okay, thank you, everybody. So, yeah, good afternoon, good morning, yeah. And yeah, today we're going to talk about net carbon-free fuel chemistry. And similar to Professor Pepio, who talked about aviation fuels and biomass, you know, most of the fuels we use today and most of the fuels we'll use in the future will still have carbon. So we think then how to reduce the carbon footprint on the overall life cycle of this fuel. And that's what I'll talk about today. How we can produce these fuels, the chemistry of production, and also of relevance is the chemistry of combustion of these types of fuels. Okay, so first thing we need to understand, fuels are going to be used in engines, yeah? And depending on the type of engine, the nature of the fuel will be different. Here's several types of internal combustion engines which have been proposed for use in transportation applications. On the left-hand side, you have your classical spark ignition engine. The defining metric of a spark ignition engine fuel is the octane number. Typically, the research octane number and the motor octane number are utilized. We'll talk more about those. We typically say we want a low reactivity fuel. Low reactivity fuel means this fuel will not auto-ignite prior to the ignition presented by the spark. So the spark ignites, the fuel-air mixture and a flame propagates, and you don't want any auto-ignition of your premixed fuel-air mixture before it's burned by the flame initiated using the spark plug. So we tend to call that lack of auto-ignition a low reactivity fuel. Also, you can say a high octane fuel. If you go to the gas station, you pay more for the higher octane fuel because it has a lower reactivity. On the other side, you have your mixing controlled combustion. This is the diesel engine. So you inject your fuel into hot compressed air, and you want auto ignition to happen because there's no spark. So your mixing controlled combustion auto ignition is driven by the auto reactivity of the fuel. And there you want a high reactivity fuel. In diesel engine terms, we call that the cetane number. If you do the lab tours, you'll see some devices that are used for measuring cetane numbers. So you typically want a fuel with a high cetane number. High cetane number means high reactivity. Low cetane number, low reactivity. So you can say the octane number in gasoline engine, the cetane number in diesel engine, they're kind of inversely related. Yeah. So one wants high cetane means low octane. And then you have some new types of engines, okay? The advanced compression ignition engines. People have talked about these a long time, for over 20 years. Homogeneous charge compression ignition, premixed charge compression ignition, so many variants. The one that's out in the market today is SkyActiv by Nissan and also Mazda's. Mazda's name is? Mazda SkyActiv. Okay, sorry, not Nissan. So Mazda's SkyActiv. And that engine operates in some kind of mixed mode. Sometimes it has a spark plug, but it's also operating in some kind of a partially premixed condition. And the type of fuel that you would use in these types of mixed mode combustion engines also is different. So bottom line is different engines, different fuel properties. How do you design the fuel with the properties that you need? And of course, if you go to an aviation turbine, it's different. Power generation, aeroderivative turbine, also you have different parameters you would look at. So again, we look at, this is a nice chart from a previous professor here at KAUST, Bengt Johansen. He highlights these three different types of engines. They're kind of 3 points on a triangle of these different types of internal combustion engines. SI engines, fully premixed, compression ignition engines, non-premixed. HCCI engines are fully premixed, but you have compression ignition and compression ignition driving the process. So in the SI engine, what are the benefits? Well, you get very easy emission control. Countries like North America went in the 1970s primarily towards gasoline engines for light-duty vehicles. And the main reason was they wanted lower emissions, lower NOx, lower soot, lower unburned hydrocarbons, better air quality. So they favor technologies going towards better air quality. And for that, you need high-octane gasoline for these SI engines. The problem is you have low efficiency because you need to throttle the engine in order to avoid phenomena like knock and destroying your engine. So the compromise there was better emissions, lower efficiency. You have then the compression ignition engine on the other side, the diesel engine. So Europe went more towards the diesel engine in the 70s because they wanted fuel efficiency. They wanted lower cost of fuel and at the expense of emissions control. So much higher efficiencies. SI engine, you're about 35, and maybe up to 40% in the best engines, but efficiency. But the diesel engines, you can get above 40% efficiency. And of course, the fuel problem here is you have more NOx emissions, more particulate matter, and the fuel you require is a diesel fuel, high reactivity. And then in the combustion community, in the engine community, we've been talking for about 25 years about HCCI engines. Try to get the both of premixed combustion and compression ignition. Try to get high efficiency by compression ignition. Try to get low emissions by premixing your charge. But the problem is it's very difficult to control this engine. Very challenging to implement in the real world. So that's where the innovations came in these types of mixed mode, partially premixed, or gasoline compression ignition. Low octane fuels, somewhere between diesel and gasoline. You can get high efficiency, you can control the emissions. The problem is none of this fuel exists in the market. If you go to the gas station, you buy diesel and you buy gasoline. You don't get this medium octane fuel, which is the best fuel actually for these new types of engines. That's where additives and maybe biofuels can actually help to augment the existing petroleum fuel. So how do we actually then design fuels for these different types of engine combustion modes? Well, the principle we use is a simulation-driven process. So here in our center, in the combustion community in general, we use numerical simulations to try to identify, okay, what is the optimal fuel composition for a specific type of engine design. And of course, for the engine design, you need computational fluid dynamics simulations. But for the fuel design, we need chemical kinetics. And that's my area of expertise. That's what we call combustion chemistry. So we start at a very fundamental level. We try to understand what are the chemical reactions that are happening under just a basic reactor condition. You take fuel and oxygen, you mix them in a reactor, and you study at different temperatures, what is the conversion of the fuel, what are the intermediates that are formed, what are the final products. And you do this in reactors that you'll see in the labs today, like jet-stirred reactors, flow reactors, shock tubes, and rapid compression machines. And from there, we start to build an understanding of what is the kinetics under which the fuel oxidizes, depending on the temperature, the pressure, and the mixture fraction. And we develop our detailed chemical kinetic models. We can then work with people to couple these models into mixing controlled combustion conditions where you have fluid mechanics. So a typical example is spray combustion is a 2D combustion system. You have a spray vaporizes, mixes with air, and combusts. And now you need kinetics, but you also need fluid dynamics to be incorporated. And we have teams in KAUST to develop the fluid mechanics, fluid dynamic models, which are then coupled with the chemistry. And then finally, you would eventually want to couple with a full engine simulation, which is cyclical, varying with time, and requires a full 3D formulation for the fluid mechanics and also chemistry to describe the kinetics of the processes. One thing to note is in the low order, zero-dimensional, one-dimensional combustion models, we can use very detailed chemistry. But as we go to more high-fidelity fluid mechanical simulations, we need to reduce the chemistry because the computational expense is significant. So all these things, if you were to take a course in chemical kinetics, you would learn how to develop the detailed models. You would learn how to reduce these models and make them available for for engine simulations. The key thing to note is, regardless of the approach, it's the fuel's chemistry that has the impact on the combustion, because that's what drives the kinetics of the process. And what our goal is, we want to understand, is what are the effects of the molecular structure of the fuel on the combustion process. So these are some different types of fuels you see here. Petroleum fuels. Petroleum fuels is made up of linear alkanes, branched alkanes, aromatics, cycloalkanes, and this determines, the mixture of these hydrocarbons determines things like the octane number, the cetane number, the flame speed, and so on. But if we go to these net carbon-free fuels or low-carbon fuels, for example, these ones derived from biomass. Professor Pepio talked about the fuels that were produced from biomass using synthetic Fischer-Tropsch processes. All of these have a different molecular structure. So typically, the ones from biomass, you have sometimes oxygenates, like this biodiesel molecule. You have alcohols. So once you start introducing these different chemical functionalities, it changes the combustion process. It changes the kinetics, which then manifest themselves in different auto-ignition, different emissions, different flame properties, flame speed, flame structure. And our objective is to try to see, for many different types of fuels, how do these structural impacts, how do these structural changes impact the combustion process? Here, for example, these different structural impacts have different effects on a combustor performance. This is a slide from Matt Colquitt talking about aviation turbines, but the same principles apply to even internal combustion engines. So you have different properties of fuels. You have chemical properties and physical properties. The chemical properties are things like the hydrogen to carbon ratio. So methane has 4 hydrogens and 1 carbon. Diesel fuel, on average, we say it's CH2, 2 hydrogens to 1 carbon. Gasoline is somewhere in between. Yeah, somewhere in between, maybe 2.1. It could be anywhere from 1.8 to 2.2 hydrogen to carbon ratio. Then you have chemical classes like the aromatics, the branched alkanes, normal alkanes, the unsaturated hydrocarbons. These will have, these are impacts on the chemical properties. You have the impurities. Sometimes you have sulfur in the fuel, nitrogen. Depending how the fuel is produced, you might also have even some inorganics like metals if they're not fully removed. And these, some other simple chemical properties that one can measure, like the heat of combustion. You do it in a bomb calorimeter. The smoke point, which is measured in a candle-like flame, where the sooting index of the fuel is determined. So these are all relatively straightforward chemical properties one could measure. Then you also have the physical properties, like the the viscosity. This is going to impact the spray formation. The distillation curve is going to tell you how the volatility of the fuel changes with temperature, critical pressure, critical temperature, density, all important physical properties of the fuel. These are things, again, you can easily measure, but it's not clear exactly how these physical and chemical properties influence the engine, because it's not a one-to-one correlation. It's non-linearly correlated due to the kinetics of combustion processes. So in combustion sense, we are concerned with things like flame speeds, ignition times, flame extinction. We're concerned with heat release, because this determines how much heat can be converted to work. We're concerned with things like particulates formation, spray combustion, even things like NOx pollutants and lean blowout. And then all of these things are a function of temperature, pressure, mixing conditions, time. And they're also a function of all of these physical, chemical properties. And that's the challenge we have as a combustion scientist, is how do you link these rather global properties with very detailed properties or detailed combustion manifestations that exist in engines. And that's where we use our kinetics. So a chemical kinetic model can be used to predict things like the auto-ignition of a fuel. So depending on the molecular structure, yeah, that depending on the chemical classes present, depending on if there's impurities, one can predict the gas phase fuel autoignition using a chemical kinetic model. So it's a direct link between fuel property and combustion property. You can predict things like the flame speed or the flame propagation rate, which is important in spark ignition engines, important in gas turbines. You can predict flame extinction and reignition, also very important in gas turbines. This we do by coupling a chemical kinetic model with diffusion controlled processes, which are determining then the flame sheet, the flame thickness, and the extinction and reignition. We can predict the heat release rate of a fuel. So as the fuel is oxidized, it's not like all of the heat is released at once. You have a series of chemical reactions. First, the low temperature chemical reactions up to about 800 K will release some heat. And then you have the high temperature chemical reactions above 1000 Kelvin release most of the heat. And then this process of how the heat is evolved can be predicted by our chemical kinetic models. People talk about ion chemistry, plasma chemistry. Chemical kinetic model can also be used to predict ions and plasma and ions in plasmas. And finally, you can predict emissions as well. So polycyclic aromatic hydrocarbons, soot formation, all of these NOx, unburned hydrocarbons, carbon monoxide, all the major pollutants, one can predict if you have this model, which describes the kinetics of how the fuel is converted to the intermediates and the final products. Now, all of these things will change again depending on the fuel, depending on the structure of the fuel. So as I mentioned in broad terms, if you have a hydrocarbon fuel like gasoline or diesel or aviation fuel, there's 4 major classes, okay, let's say 5 major classes of fuels. You have the alkanes. These are the straight chain hydrocarbons. You have the branched alkanes, which are straight chain hydrocarbons with some branches. You have the alkenes, or sometimes people say the olefins, things that have double bonds, straight chains with double bonds in them. Then you have the aromatics, the cyclic ring structures, which are unsaturated. And then you have the cycloalkanes, which are the fully saturated ring structures. And these 5 hydrocarbon classes will vary in every kind of fuel, yeah? So what do you guys think? Anybody can tell me which one of these classes gives you a high autoignition or more reactivity? Of these 5 classes I mentioned, can anybody think which ones would give us more reactivity, better autoignition? Alkane. So this is straight chain hydrocarbons that will give us most of the reactivity in terms of autoignition propensity. And something like an aromatic will give you a low autoignition tendency. So if you want a fuel with a high octane number, we know right away, put more aromatics. Yeah? And same with cycloalkanes, same with alkenes. How about flame propagation? If you want a high flame speed, what's a better class of molecules to use? Aromatic, not such a high flame speed. Typically, alkenes, yeah, will give you a higher flame speed. And also alcohols, yeah, methanol, ethanol are pretty good for giving you a better flame speed. Extinction, reignition, so extinction also, you're better off with lighter hydrocarbons, which are alkanes. How about emissions? What's going to make all your PAH and soot? Aromatic, yeah? So more aromatic. You put aromatic in to give you better ignition performance, but then you're going to get more soot. So this is a compromise, right? So this is the challenge that we have. We need to balance then, and all fuels actually, you have a limit on the aromatic. So typically it's around 30%, depending, anywhere from 25 to 35% aromatic is the maximum you can put in a fuel because they don't want the fuel to have too much of a sooting tendency. So these are what a person in a refinery that's blending a fuel would think about. If they want to produce a fuel with some properties like octane numbers, emissions profile, they would start to think, okay, how do I blend these different hydrocarbon streams to give me the properties that I want? It works, it's a good approach, but if you want to really tailor the engine, you want to be able to predict these things using a numerical model. And it's not enough to just say, put in more alkanes. We want to know exactly how many alkanes we put in, the structure of those alkanes, what is going to be the impact on the engine performance. And for that, we need our kinetic models. And that's what we do here at KAUST, okay, and in the combustion community. We know how fuels are being produced from petroleum. We characterize these different classes of hydrocarbons like alkanes, branched alkanes, aromatics, olefins, cycloalkanes. We do experiments. You'll see these experiments in the labs, these kinetic experiments to understand how these different molecular structures impact ignition, how they impact flame speed, how they impact emissions. And we build the models, the kinetic models, to predict those experiments that we have measured. And finally, we can combine these kinetic models with combustion property prediction in actual engines. So let's talk about this more. This is typically what we'll see if we're going to take a fuel and study its properties at a global level and at a compositional level. So first, this is an example for a gasoline. If you're going to go to get the gas station and get a gasoline, or you can ask the supplier for a certificate of analysis. Certificate of analysis are standard tests which describe that this gasoline fuel meets a certain specification, a specification that by regulation, one would allow you to sell that fuel as gasoline. So the certificate analysis actually tells you the limits. These are the limits that the regulation prescribes. And I think here we have a Euro 6 fuel, okay? So a Euro 6 fuel has a certain specification for the gasoline based on the European standards imposed by the regulatory bodies. And it says, okay, you could have a minimum and a maximum. For example, research octane number has to have a minimum of 95. There's no maximum. They say you can have whatever maximum you want. Similarly, the motor octane number, minimum 85, but no max. So if there's no max, is it better to make it higher? Why not? More expensive. So nobody wants to increase the octane number more than you need to because you got to add in more expensive components from the refinery to get there. Yeah. So this fuel, the result is 97.5. They've actually exceeded the RON spec, but they did that because they needed to get the MON spec above 85. And then you have other things, density, vapor pressure, aromatic concentration here you see is anywhere between 29, max 35, so they put 30.5. Benzene, you're not allowed to have much benzene. So here you can see it's already, this should be in ppm, so about, yeah, it's about 0.4 ppm, which is under the regulatory limit. And then you have other things, the hydrogen to carbon ratio, oxygen to carbon ratio, some impurities like lead, sulfur, phosphorus, and even ethanol is an additive. So if you get the fuel from the supplier, you can get these details. This is typically not enough to predict exactly how the fuel will behave. It's enough to operate your engine. Okay, you can operate your engine comfortably. You know the engine won't knock, you won't destroy the engine, but it's difficult to predict exactly, okay, what is going to be the flame speed, what is going to be the auto ignition, what is going to be the emissions profile of this fuel. For that, we need to know in detail all the hydrocarbons. And for that, we use something called detailed hydrocarbon analysis. It's a gas chromatograph, which separates all the hydrocarbons and then sends them to a mass spectrometer or a flame ionization detector to quantify and to detect the different molecules. And you can see this fuel, which had these global properties, actually has about 200 different hydrocarbons. And that makes it very complicated then to deal with. There are 200 different hydrocarbons. And this test, nobody gives it to you right away. So if you go to the supplier, they're not going to give you a DHA because it's expensive to do it. They need standard equipment. So it's a research tool that we are using to understand the fuel more. And then how these things are linked to these global properties, one needs to develop an understanding of that using kinetic models. And as Professor Hareen mentioned, the way one way we do this is through surrogates. Again, 200 molecules in the gasoline. There's no way I can develop a kinetic model. I'll be here for the rest of my life and your life as well. Typically a kinetic model, a good one, a detailed model. I worked at a place called Lawrence Livermore National Lab. They pioneered in the 1980s the development of these kind of detailed chemical kinetic models. For one molecule, it takes, probably about 1.5 to 2 years. And then that's still only the first iteration. Then from there, you're iterating and improving. You can take, for the standard fuels like heptane and isooctane that are used in gasoline, we have pretty good chemical kinetic models today, but it took about 10 to 12 years, to get there. And then that's, again, when we have 200 different hydrocarbons, there's no way we can reliably develop the kinetic model. So one is the time it takes to build the models, right? The second is, even if you had the model, let's say we had an AI that builds all the models for us. We're working on that, by the way. It's possible to build an AI that will build the kinetic model. But then what? The model is so detailed, there's so many reactions, so many species, you cannot solve all these equations, So again, for a molecule like N-heptane or isooctane, your standard fuel, gasoline fuel surrogates, those models have about 2,500 species and about 7,000 reactions. In a CFD simulation, you can only afford about maximum 100 species. So from 2,500, we have to come down to 100. And again, for a fuel that has 200 components, very difficult to do that for every component. So that's where we do something like surrogates. Surrogates, you'll take a representation of these 200 hydrocarbons, and you'll build a subset. And for example, the typical approach we have for this is we just choose the different classes I mentioned. Aromatics, we choose a couple of aromatics. We choose a couple of alkanes, some branched alkanes, and some unsaturates, so cycloalkanes and alkenes. And the general concept here is we're trying to build some representative components. And you see here we have N-heptane for representing the alkanes, cyclopentane to represent the cycloalkanes, toluene and trimethylbenzene. There's no right answer. There's no one answer you can say. This surrogate is the only unique surrogate for a fuel. It's an approximation that one makes to match. We're trying to match the octane number of the fuel. We're trying to match these overall hydrogen to carbon ratios, olefin concentration, aromatic concentrations, and we're trying to match what we see here, kind of a distribution of hydrocarbons. So this x-axis here is retention time, but you could also think of it like molecular weight. So these are light hydrocarbons, and these are heavy hydrocarbons. So you want your surrogate also to have light hydrocarbons and heavy hydrocarbons. And hence what you can see here is you have structures which are a range of molecular weights. We have toluene as a light aromatic, trimethylbenzene as a heavy aromatic, N-butane as a light alkane, heptane as a heavy alkane. So you try to spread, similar to your distribution of hydrocarbons in the DHA, you try to spread your hydrocarbons across different molecular weights. Now we have computational tools to do this. We have a website, Cloudflame. You can go to the website. If you know the composition of your fuel, it'll make your surrogate for you and provide you a kinetic model for that surrogate. And then we can use this surrogate to predict or to either see how an engine will behave or to design a fuel. We heard previously about the COOPTIMA program in the US Department of Energy. The COOPTIMA program tried to design fuels for light-duty spark ignition engine. And they do that using what we call a merit function. This is a merit function. Merit function, you can say, higher the merit function, better the fuel, okay? So the merit, or the better the engine will operate, okay? And this merit function depends on some of these properties. One is the research octane number of the mixture, and then some constants are there. S is the sensitivity, which is the difference between the research octane number and the motor octane number. The heat of vaporization, the air-fuel ratio of the mixture, even the flame speed, okay? So it's a complex equation. It's designed, this equation is made for a specific engine. and it says for this engine to operate the best, let's make a fuel that maximizes this merit function. And how can I make that fuel? Well, I can develop kinetic models for individual components. I can predict the laminar flame speeds. I can predict the octane numbers by means of understanding their auto-ignition tendency. And then you can optimize the fuel for the engine. So this is what the co-optima program tried to do. They tried to use chemical kinetic models to screen many different molecules. And they found things like alcohols, unsaturated alcohols, some aldehydes and ketones are potential good additives that one could use inside of gasoline fuel. So this is a general approach. This is the approach we apply to hydrocarbon fuels if we want to design the fuel. Now, what if we want to take this approach and use it for biofuels or low carbon fuels? Can we do it? So first thing is, what are these fuels? What are the fuels that are lower carbon footprint? Do they look the same as gasoline? Do they look the same as petroleum? Or do they look different? Well, what do you guys think? Fuels that are lower carbon or say net carbon free, do you think they look the same or they look different in terms of chemical structure? Same? Okay. Who says they look the same? Okay. Who says they look different? Okay. Why? Okay. Both of you are right. Okay. When you say the same, what do you think it'll look like? Yes. Okay. Oh, true. Yes. So one point is, okay, he's saying ethanol, methanol. Doesn't matter if it comes from biomass or if it comes from oil. It's the same ethanol or methanol. That's true. One thing, the difference there would be alcohols are not common in petroleum-derived fuels. Yeah, so typically when we produce petroleum-derived fuel in the refinery, we're not making ethanol for additive. We're mainly using, we use MTBE here in Saudi, methyl tert-butyl ether. And in North America, the ethanol is coming from biomass sources. They use octane enhancer. Or they'll use aromatics to improve the octane. So typically when gasoline fuel is typically non-oxygenated. No oxygenated molecules are there. But because of biofuel regulations, they started to add more and more ethanol into the mixture. So then when you guys say they look different, yeah. So they also can look different because you make alcohols, you make different hydrocarbons. But I'll show you, they can look the same too. Depends on the process you use to produce your fuel. That's what matters, not really the nature of the feedstock. Okay, so these, we say net carbon free. This is the traditional net carbon free fuel is biomass derived fuel. So you're taking a renewable resource like biomass. So biomass takes CO2 out of the atmosphere. It takes sunlight, it takes water, it makes sugar. And then this sugar is a feedstock for producing your biofuel. Or it could be, besides sugar, you can use oil, like an oil seed. You make biofuel, you use it in the vehicle, you burn the fuel, and then you get CO2 back, and it goes back to the atmosphere. So they say it's net carbon free. Is it really net carbon free? No? What are the issues with the biofuels or this approach? Okay. So you have to grow more plants, but growing more plants means you take more CO2 out of the atmosphere, right? Isn't that better? Huh? What do you say? Walking, you need a lot of water, sure. Okay, what about deforestation? So actually, we come to the, okay. People said fertilizers, transportation, of course. The transportation is burning fuel. So if you're using fuels that are from hydrocarbons to transport biofuel, that adds to the carbon footprint. Somebody said fertilizers. If you need fertilizers, you got to make fertilizers from petroleum. Yeah, urea comes from methane. Yeah, nitrogen-based fertilizers come from steam methane reforming, and other types of fertilizers use a lot of hydrocarbons to produce. Similarly, the machinery that one uses for farming is powered by diesel or by petrol. that all adds to the carbon footprint. Okay, so before 2008, people used to do these types of studies. They look at the amount of fertilizer needed, the amount of diesel machines that are needed, the amount of transportation. And they said, okay, these biofuels are about, they do have some carbon emission, but they're typically 80 to 90% lower carbon footprint than petroleum-based fuels. But then in 2008, something happened, yeah? And somebody mentioned it, deforestation. People started to look not at just what it takes to grow the fuel, but the land use requirement. We called it land use change at that time. There was 2 pioneering papers in Nature and Science around the same time that started to calculate the land use change for producing biofuel. And the general idea is, if I have a forest, that forest is already a carbon sink. A rainforest, for example, in Brazil. It's sucking a lot of carbon out, and it's storing carbon there for thousands of years. If I cut it down and replace it with a farm, well, that farm has a much lower carbon sink potential than the initial rainforest. And as well, by cutting down the rainforest, you've released essentially thousands of years of carbon storage potential, yeah? And that land use change, one is called indirect land use change, one is called direct land use change. You can quantify both of them. If you add that up, actually biofuels in many cases produce more CO2 emissions than petroleum fuels because you've lost a massive sink of carbon in the environment. So these were the debates. And then in 2008, people started to think, okay, are biofuels good or bad? Well, a lot of the regulations around biofuels started to change. In Europe, a lot of the biodiesel was coming from Malaysia, and they were deforesting the rainforest to plant palm trees, palm oil, and that was causing not only, of course, devastation to the environment, but also didn't do much for the carbon footprint. So we started to think, okay, can we do different things? The conventional biofuels, first generation, you take biomass, you're basically taking the sugar in corn, in sugarcane, or the oil in soybean. You either do a fermentation process or a hydrolysis process to make your biofuel, and you make 2 things, biodiesel or bioethanol, your classical first generation ones. Then people started to say, if I'm only taking the sugar, about 90% of my biomass is wasted. If I take sugarcane, the sugar is only one part of it. The rest of it is the leftover biomass. They call it the bagasse. So the lignocellulosic biomass, can we turn that into fuel? Yeah, well, you do biochemical or thermochemical means. You can make some fuels from these lignocellulosic feedstocks. Now the future, they're saying, is from algae. Everybody talks about microalgae for the past 10 years, probably more, 15 years, as being a feedstock for biofuel production. Because microalgae, they don't require land. You can grow them in ponds in the desert or in the middle of the outside, on the outskirts of a city, on the ocean. And then these algae will make oil, they'll make sugars, and you convert that to biofuel. And 4th generation, where you do genetic engineering. And we have some colleagues here who do this as well. They engineer your algae or your microbes to produce specific types of hydrocarbons and then use that for fuel. So anybody here know about microalgae derived fuel? Is it feasible? Is it promising? What do you guys think? Anybody have thoughts about that? Microalgae? Huh? In what? Yeah, okay. So I mean, in a natural environment, algae results in eutrophication. Yeah, so it depletes the oxygen in the pond. So of course, in a natural environment, you don't want too much algae, but I'm talking about industrial production of algae. So algae is a microorganism. It grows in water, sometimes seawater or fresh water. It produces oil, its own oil. It produces sugars. And you can potentially use this to make biofuel. The concept exists. Okay, and here you see here microalgal biomass. If you make this biomass, you can convert it biochemically, fermentation, anaerobic digestion. You can make different types of fuels, even hydrogen. You can do thermochemical conversion. You can either burn it, you can liquefy it, gasify it. You make different types of hydrocarbons. You can do transesterification, a chemical conversion to make biodiesel. So many different fuels can come from this one feedstock, depending on how you treat it. And the problem is, where do you get the feedstock? And there's always a problem with any biomass or biofuel-related activity. So algae is grown in a pond. If you guys have a chance in this week, you can go out to, what do we call that? KAUST Research and Technology Park, KRTP, okay? Actually, if you walk out the doors here and you take a left, and you walk for about 7 minutes, you'll see algae reactors out there with these tubular reactors where algae is growing, and they're doing demonstrations on algae production. And then we're also building a 100-hectare algae farm in raceway ponds. That's about 10-minute walk if you walk to your left. So it's feasible. You can make algae. The problem with algae is you grow it in water, and typically the algae is only around, by the end of it, you have algae, which is about 5% of the total mass of the wet mass of the water. So you have 5% algae, 95% water, and you got to separate these things. And it takes a lot of energy to separate a small amount of algae from a lot of water. That's one issue. And other thing is, if you can grow algae, the last thing you want to do is make fuel, because algae has much higher value in other places. One thing is algae is used in cosmetic industry. Yeah, a lot of cosmetics are using the omega-3 fatty acids in the algae. Also, it's a great feed for livestock and animals. So actually, our colleagues here who are building a big-scale microalgae facility, they're not going to use it for fuel. They're going to use it to make feed for chickens, because that's where the value is, yeah? Not for fuel. Fuels are too cheap. So we need other approaches to make low-carbon fuels. My view is, and the view of many people is, biofuels are limited in their application. We may, in the end, save them only for aviation, because it's sometimes the hardest to decarbonize sectors. So we need other options for road transport. So that's where we come to e-fuels, okay? And I want to talk in the last 20 minutes or so, half an hour. How do we make these e-fuels? And what are the challenges with the production of these e-fuels? So again, biomass, as we showed with the algae, you can do different things to biomass. You can make a synthetic fuel. E-fuel we'll make from hydrogen, which comes from water, and carbon dioxide, which comes from either point source or the air, and we'll make a hydrocarbon fuel. We'll talk more about this process. And okay, the title should not be types of biofuels. These are types of net carbon-free fuels. You can make alcohols. You can make esters. If you do some different treatment, you can make ethers, aldehydes, ketones. People are looking at that from genetic modification of biomass. Enols, or unsaturated alcohols. Even you can make other types of hydrocarbons. You can even make drop-in hydrocarbons. And you mentioned that fuels derived from biomass can look exactly like petroleum fuel. You can make alkanes, you can make aromatics, you can make branched alkanes and olefins. You can make whatever you want, actually, from biomass, or even from synthetic e-fuel. Of course, it takes more chemical processing depending the type of material that you want to produce. But the trend nowadays is, well, what do you guys think? Is it better to make these types of molecules, alcohols, esters, ethers, or is it better to make drop-in hydrocarbon? Okay, why do you say drop-in is better? Okay, so one thing is I spent a lot of money designing my engines for petroleum fuel, which has aromatics, hydrocarbon, alkanes, isoalkanes, and I want any other fuel to be readily compatible, right? And I don't want to redesign my engine now for new types of molecular classes. That's add a lot of expense, and especially when we have billions of vehicles out there, why not just use make something that looks the same as the petroleum fuel, and then you just use them as you go, right? So one is the vehicles, right? The engines are designed, the vehicles are designed to use a specific type of fuel. So if you can make from synthetic means, either from e-fuel or from biomass, if you can make the same type of hydrocarbons, that's good. It has a benefit. Why would you want to do these other ones? Well, sometimes the engine can be better if it runs on alcohol rather than hydrocarbon, yeah? Is Professor Turner here? No, he left, okay? But he loves the methanol engine. Because methanol is actually a great fuel. So is ethanol, high octane, good flame speed, yeah? These are good fuels for automobiles. 100% methanol engine, it was used in IndyCar racing. Right now, IndyCar uses 100% ethanol. A good fuel, yeah? And it can come from biomass, it can come from e-fuel, as we'll see in a bit. But why don't we use, what's the challenge? Well, say again? Corrosion. So there's some issues with compatibility, right? So the lines, the polymers that are used in, the seals that are used in existing vehicles, they're not really compatible sometimes with alcohols. But there's a company, Geely. Anybody heard of Geely? China. They have something like over 100,000 methanol vehicles already running in China. They make it from coal. So they just change the lines, and they change the seals, and they run their vehicles on methanol. In Brazil, they use a lot of ethanol, right? How much is the ethanol concentration in Brazil fuel? Huh? 85? Tiago, do you know? I think they even have 100% ethanol-fueled vehicles in Brazil. Flex fuel is 85%. But in Brazil, they have even 100% ethanol. And they make from biomass. So you can do it, okay? What I hear in the US is the major challenge is they can change the vehicles. But the problem is not only the vehicle, it's the fueling infrastructure. This is the hardest part to change, actually. So again, the combustion community did a lot of work on new types of fuels for engines, and then they went to the market, and they said, okay, we want to deploy more ethanol, more methanol into the supply chain. And they said the infrastructure can't handle it for the same reason, the seals. Yeah? And actually, the major problem was in the gas stations. The gas stations have underground storage tanks, and these underground storage tanks are sitting there for like 50 years, 60 years, and they have very old materials which were made for hydrocarbons. Once you put some alcohols in there, you'll corrode those fuel tanks, the fuel lines. They'll start leaking into the ground. It won't be good. And the cost to change those fuel tanks is not cheap, yeah? And most fueling stations in many countries, not here in Saudi, but in Europe, in North America, they're owned by small business owners. Like they call them mom and pop shops. Fuel stations are franchises which are owned by individuals or groups of individuals. They can't afford to change all the infrastructure. That's the reason it became very hard. It was hard to change not only the engines, but also the entire infrastructure for delivering the fuel. And that's why people now look for the drop-in. If we can make in a centralized facility something that looks like the current petroleum fuel, it should be the easiest to deploy. If the carbon footprint is low, it's a win-win for everybody. So how can we do this? The approach we look at here in Saudi is using renewable energy. So I want to talk about this, the chemistry of converting renewable energy into liquid fuel that can be used in different applications. Yeah, either in light-duty vehicles, we call these power to liquids, even power to gas, hydrogen as a fuel as well. So power to liquid or power to X, we can make different things, okay? And we've already heard about some of these in the presentations earlier this week. You can make hydrogen. I'm going to talk about, though, the issues or the challenges with making hydrogen from renewable energy. You can make ammonia. Ammonia is great because there's no carbon, but is it carbon-free? Actually, I'll show you it's not really carbon-free. Even though there's no carbon in ammonia, when you make the ammonia, it can have some carbon emissions, even if it comes from renewable energy. You can make oxygenates like methanol and ethanol. I'll show you a process for that. And you can make drop-in fuels also. Yeah? You can make something that looks just like gasoline. And we'll talk then what is the chemistry required to make all these things happen. So let's start with hydrogen. Regardless of all of these need hydrogen to start out with. Yeah? The feedstock for any type of low carbon, net carbon-free synthetic fuel from renewable energy is hydrogen. And hydrogen, you've heard about different colors of hydrogen maybe. There's a whole rainbow of colors of hydrogen. It's a colorless gas, but it's the only colorless gas which has a rainbow of colors attributed to it. Yeah? So the classical one is gray. You make hydrogen from methane reforming, and then that's shown here. It has a lot of CO2 emissions associated with it. You could also make hydrogen from coal, which is what they do in China. A lot of CO2 emissions related to that. Now, here in Saudi, we want to do what we call blue hydrogen. Aramco wants to make blue hydrogen. You take methane, you reform it with steam, and you capture the CO2, and you put the CO2 underground. So you can typically capture about 85 to 90% of the CO2, and it only costs you about twice as much as gray hydrogen. So gray hydrogen costs about $1 a kilogram of hydrogen. Blue hydrogen today costs about $2 a kilogram. And then you have yellow. I don't even know what yellow is. I still don't know what this one is. Pink, I know. Pink is from nuclear. If anybody knows what yellow hydrogen is, let me know. Orange is what? I think yellow is the grid. Yeah, grid. White. Okay. So this is not all of them. Pink is from nuclear, so using nuclear energy to make hydrogen. Again, pink hydrogen still has CO2 footprint because of building the nuclear facility. And then green hydrogen is the ideal one, the lowest carbon footprint from renewables. And that's the one I'm going to talk about today because, well, first of all, if you're making fuel from fossil fuels, people talk about making blue hydrogen and using that to make a low carbon fuel. Doesn't make much sense, yeah, because if you have a fossil fuel, better to make a fuel directly rather than making hydrogen and then converting that hydrogen back into a fuel. Just use the fossil fuel in the first place. It's much more efficient. But if you have renewable electricity, yes, you want to make it hydrogen, and you want to use that hydrogen to produce a fuel. So how do we do this? Electrolysis is a process. Different types of electrolyzers exist. You take water, is H2O, you split the oxygen off the hydrogen using electricity. You need 2.3 electron volts to do this. And you can do this by different types of electrolyzers. They all do similar kinds of things, okay? You have a cathode and an anode, you feed water, you apply a potential, and you evolve hydrogen and oxygen. The three different kinds, one is called alkaline water electrolyzer, the other line is PEM electrolyzer, polymer electrolyte membrane, and then the solid oxide electrolysis cell. So these are the two, if you go out on the market, you'll see today. You can buy an alkaline water electrolyzer, you can buy a PEM. They operate around low temperatures, 90 degrees Celsius or so, maybe 100. The SOEC operates around high temperatures. The advantage of the PEM is you get higher current density. So the amount of hydrogen you can make per unit area of electrode surface is higher. So the footprint of your plant is smaller, you can get higher efficiencies. The SOEC is also very high efficient, but you need a high temperature. Operating a unit at 700 C is hard because things fail at high temperature. You need special materials, you need special seals. So always better to work at low temperature. I skipped this one. So when we talk about these different electrolyzers, so the first is alkaline, the second is PEM, the third is solid oxide. So this is what it takes to split water. This is the specific energy, kilowatt hours per meter cubed of hydrogen. To split liquid water, up to about 100 degrees C, you can see the specific delta Gibbs free energy that's required. You can see it's an endothermic process. You got to feed in energy to drive this process. If you convert the liquid water into gaseous water, the Gibbs free energy drops. So that's why if you operate in SOEC, it's much more efficient because you have a lower Gibbs free energy of reaction. If it's operating with liquid water, like in a PEM or an alkaline system, the efficiency is lower. So if you see here, SOEC is 90% efficient, but an alkaline system is only 70% efficient. A PEM is somewhere in between, about 80% efficient. Now, the question is, when you're building a facility, say I want to build an e-fuel facility, should I build a facility that's very efficient, or should I build a facility that I can scale up to very large scales, yeah? The alkaline systems are pretty easy to build. We've been building them actually for about 100 years. People know how to build alkaline water electrolyzers. There have been companies in Europe and South Africa which have made these 20 megawatt unit. Okay, so that's a big electrolyzer, 20 megawatts. PEM electrolyzers, they're newer, they're more expensive. You're typically limited, now the biggest ones are about 3 megawatts. So again, you need 20 PEM electrolyzers just to match with one alkaline system. And SOEC, it's only around 1 megawatt. So efficiency is an issue, scale is an issue. Well, what would you guys choose if you're building a large facility? Scale? Okay. Why? Huh? Scale with reasonable efficiency. Okay. Well, one thing I keep in mind is efficiency is what? Of converting electricity to hydrogen. And where's the electricity coming from? Renewable energy, wind farm, solar farm. So efficiency losses are translating into more cost in your renewable energy power plant, right? Because you got to build more energy for the same amount of hydrogen if you're using a lower efficient device. Okay. But scale, why would you want scale? Because if you want to reduce cost, the best way to reduce cost in an engineering project is go to bigger scale. Small scale plants per unit of hydrogen produced are incrementally much more expensive than a large scale facility because your CapEx typically scales by power 1.6. Yeah, we call this the 6/10 rule in chemical engineering. So for every, if you want to scale up a facility, you can make it 10 times bigger, the cost is only six times higher. So incrementally, the cost is per unit of hydrogen is better as you go to big scale. And in Saudi Arabia, the project in NEOM, we're trying to get 2 gigawatts of energy. So we need 100 of these 20 megawatt electrolyzers, or you need 2,000 of these 1 megawatt electrolyzers. So a 2 gigawatt facility, you go for scale. Yeah, you need to produce a lot of hydrogen, 650, 700 tons of hydrogen a day. We go for scale. We don't care about efficiency today. And then you have to compress. You lose some energy in compression, but only about 10 to 15%. Some people say, oh, hydrogen needs water. Yeah, it needs water. 1 kilogram of hydrogen requires 9 kilograms of water. So if I'm making 1 ton of hydrogen, 1,000 kilograms of hydrogen requires, let's say, 9,000 kilograms or 9 tons of water, 9 meter cubed of water. It's not that much, actually. You guys use much more water taking a shower, flushing the toilets, and growing your food. Actually, most of the water we use today is for growing our food. So freshwater requirement, 9 kilograms for our facility in NEOM, 650 kilograms per day. We need 6,000 meter cubed of water. That's a small RO plant. The city of Jeddah has 1 million meter cube of water daily production. We need only 6,000. So these are the things you can think about. Some people in Saudi here, we have to desalinate the water. You need to take out all the salt because we don't have fresh water here. So taking out the salt or desalinating water requires energy. And some people say, oh, we should do direct seawater electrolysis. So we don't have to desalinate the water. We just electrolyze seawater directly and make hydrogen. But if you see, it's inconsequential. Hydrogen has 33 kilowatt hours per kilogram. My efficiency is 70%. I need about 50 kilowatt hours per kilogram of hydrogen. But for 1 kilogram of water, it only is 0.003 kilowatt hours. It's inconsequential. It's 1,000 times less energy to desalinate water compared to splitting the water. So again, in the overall capex of this facility, I think the desal plant doesn't even show up. It's like 0.25% to build the desal facility. All the cost is in the renewable energy and is in the electrolyzers. So again, you're thinking about where to do research, forget about seawater electrolysis, okay? Because the cost benefit is not even worth it. We know how to desalinate very efficiently. Okay, this is a project I showed you guys in NEOM. 2.2 gigawatts, so I need 200 electrolyzers. Sorry, 100 electrolyzers, 20 megawatts each, or 110 to be exact. This is powered by 1.2 gigawatts of wind turbines and 2.2 gigawatts of solar. All of this hydrogen is going to make ammonia, and then ammonia is going to go to a ship and be sent to different countries around the world. About 3,500 tons of ammonia per day. Why they want to make ammonia? Because, well, I think you've heard over in previous discussions, it's easy to ship ammonia. It's not easy to ship hydrogen. And again, the plant will be ready in about 2.5 years. It'll start shipping ammonia by 2026. And this facility runs 24/7, the ammonia plant. You can't shut down an ammonia plant. It's 350 bar, high temperature. You don't shut down this facility. The electrolyzer is not making hydrogen all the time. It only makes hydrogen when the wind is blowing and the sun is shining. So that's why we need a buffer facility. We need to store some hydrogen, about 120 tons, to continuously feed the ammonia plant. So now I'm going to talk to you how you actually design this facility, because we've talked a lot about ammonia combustion utilization, but how do you build a green ammonia facility? Where do you build it? Where does it make sense to build it? And of course, you build it where it makes the lowest cost. And what determines the cost? It's the renewable energy that goes into making the hydrogen. By the way, this facility, 2.2 gigawatts of electrolyzers, is about $2.5 billion. 4 gigawatts of renewable energy to power the wind farm turbines, power the electrolyzers also for the ammonia plant. So this is a overall $7 billion project. There's about $6 billion spent on the renewable energy. $5 billion spent on the renewable energy, $2 billion on the electrolyzers, and about $1 billion on the ammonia plant. So that's an approximate split. It's about $8 billion project. So most of the cost is the renewable energy, right? The second biggest cost is the electrolyzers. The third biggest cost is the making of the ammonia. Once you have hydrogen making the ammonia, we know how to do it, and the technology has been around. So first thing, I need to pick the best site. So we look around the world. Well, I don't look around the world. I looked here in Saudi, okay? Where is it the best to build a renewable energy facility combining wind and solar? So you look at some maps. These are installation maps of solar energy across the country. You look at wind as well, wind maps. And we picked 3 different sites for this study. We say, okay, the Northwest is shown here. This is where NEOM is. We can look in the east where Dammam is and Aramco, and you can look in the west as well in Jeddah. You can see here solar intensity is higher in the Northwest. That's because there's less cloud and dust in that region. So already from a solar perspective, it's looking a bit better, but okay, it's not enough to just look at this map and say that's enough. And then wind profiles as well. You want wind to balance off the solar, so you can look at the wind profiles as well. So we actually get this information from satellite data, and we develop these what we call violin plots for the 3 different sites. So we have some monthly variation in solar, wind, and in these different sites. And this determines the capacity factor, okay? So you can see here for the central site, you can have capacity factor, renewable energy down to sometimes 15% in some months, but peaking up at 35%. In the Northwest, the red curve has much higher capacity factors. And then you also look, in order to design your facility, you look at these violin plots, the daily variation and the monthly variation in these energy profiles. So again, for wind, you want a site which has less variations, because the less variation that you have, the less dynamic changes you'll have in your electrolyzer operation. So you preferably want constant wind, constant sun as long as possible, yeah? So you don't have to change the dynamic operation of your facility. So then the Northwest typically has the ideal, well, has a more balanced load profile for daily profiles as well as for monthly profiles. So we look at these different sites. We do this, then we look at the same thing for solar. Solar, again, central, northeast, northwest. We look at the profiles, and we feed all this information into a model, okay? The model includes the renewable energy generation, the wind and the solar. Using those profiles that we have, we can have a simple model which says, with this wind profile, with this solar profile, this is the amount of megawatt hours we'll get as a function of time. We know the capex of wind and solar, about it's almost $1 a megawatt for wind, about $0.5 a megawatt for solar. You need your electrolyzers. We know the cost of these electrolyzers. You need some storage. You need air separation unit to make the nitrogen. You have an ammonia plant. And you might also have some battery and some fuel cells for backup. So we build a model. The model is a techno-economic, but also an operational model. It tells us the cost of each of these units. It says, if you vary the renewable energy, okay, how do I have to size my electrolyzer accordingly? How much hydrogen storage will I need? How much ammonia will I get out of the system? And then we specify an objective function that says design the plant size to give me 3,500 tons per day of ammonia, and balance the cost of all the other things based on an objective function. And then we can determine the cost of the ammonia that comes out. And we see here, I won't go into the details of all of this, but just these types of models. Let's take the Northwest site. It has the lowest cost, anywhere from $350 to $400 per ton of ammonia. You see the major cost factors are the wind and the solar, about 2/3 of the cost. And then the other remaining costs are these electrolyzers, which are shown in the blue. And these kinds of models are what we use. Okay, these are the models we use to determine what's the best site, how do we size the plant accordingly. And these are the kinds of models that were used to make the financial decision to invest into a plant in NEOM. Similarly, you can do the same kind of study in other parts of the world. You could do it in other regions. The main point is you choose a site which is the lowest cost. Yeah, well, here in Saudi, we don't worry about permitting. In other countries, you would worry about permits. But here, we can get the permits if the cost is right. Yeah. Now, you make the ammonia. The idea is to take this ammonia and to send it to Europe. And actually, in Europe, they're not going to sell the ammonia to power the engines. They're going to crack the ammonia back to hydrogen, because hydrogen is more valuable than ammonia. Now, that comes the carbon footprint. In order to sell hydrogen in the RED II in Europe for a premium, you need 70% carbon savings compared to the benchmark. The benchmark is 94 grams CO2 per megajoule. For ammonia, it has to be green hydrogen has to be 70% lower CO2, so it needs to reach 28 kilograms CO2 per megajoule. When I make the ammonia here in Saudi, there's always some residual emissions, because we have to, of course, have a backup grid for the electrolyzer. It's not totally zero carbon footprint. I'm introducing about 30 to 39 kilograms of CO2 per kilogram. If I transport this ammonia by sea, I'm emitting some more CO2 in the transport of the ammonia, 65 grams per kilogram of ammonia. Then when I get to the port of Rotterdam in Europe, I need to move the ammonia by road to the end user facility. That road is still powered by diesel fuel. Then I need to crack back the ammonia to make hydrogen. That requires energy. If you do this in Europe, you're going to use the grid, or you're going to burn natural gas. If I burn natural gas, well, I have more CO2 emissions. And finally, I need to compress the ammonia to 700 bar, compress the hydrogen to 700 bar to feed to a vehicle. And that also requires grid electricity. So in the end, most of my CO2 footprint comes from the end, in taking the ammonia, cracking it back, and then compressing the hydrogen. And in total, you see this facility with this entire chain that we've calculated is about 33 grams CO2 per megajoule. It doesn't even meet the RED II standard. So we need to do some savings along here. So what people propose, okay, burn some of the ammonia in the cracking process rather than burning natural gas. That'll lower the carbon footprint. or power this compression by renewable energy. That will lower the carbon footprint. Well, I think there's a better idea. You guys know what it is? Huh? Yeah, burn the ammonia directly. Forget about this cracking and compression. Just burn the ammonia directly. And that's what you guys heard about the last couple of days, yeah? So I think really the case for ammonia economy will be in direct combustion in the places where it makes sense. So power generation, maybe in vessels, because this scheme is going to be very hard to meet the road standards, even if you make it back to hydrogen. Okay, the last thing that I talk about are, so we talk about ammonia. What about methanol? We can take, I just have a few minutes, right? 12:20 or 12:15? 12:15, okay. So we can take hydrogen, and we can also react it with carbon to make different fuels. We can make methanol, ethanol. We can make hydrocarbons as well. So to make methanol, we take hydrogen, we split it. Then we react this hydrogen with CO2. And then we mentioned here reverse water gas shift. You get CO. Then you react CO with hydrogen to make methanol. This last step is exothermic, but the first two steps are endothermic. The overall process uses CO2 and water, which are low-value reactants, but it requires a lot of energy. So that's where the cost goes in. Okay, this process sounds great, but okay, the problem is, where do you get CO2 from? You can capture it from somewhere, right? Or you can capture it from air. Air capture is very expensive. Capturing from point source is much cheaper, yeah? But then you need to still purify it. And I don't like this process because, well, you take water to make hydrogen, but then I react hydrogen with CO2 to make water. So I've wasted hydrogen. That's why I like ammonia much more, because you don't waste your hydrogen. Here you waste hydrogen to make water back. And then of course you make even, we'll show later on when you do MTG process, you even lose more hydrogen. Yeah, but this is what it is. I'll skip the video because of time.
Human activity.
But that's a plant in Iceland which has already produced from CO2 and hydrogen methanol. This is a facility in Neom. Take hydrogen from an electrolyzer, react it with CO2 to make methanol, store the methanol, and then convert that methanol to gasoline. Now the challenge with this facility is you need hydrogen. Hydrogen is expensive, right? Coming from electrolyzers. Okay, we might make it cheaply if we have very cheap renewable energy. Then I need CO2. For a big methanol plant, I need 14,000 tons. For 10,000 tons in the methanol, I need 14,000 tons of CO2. That's a lot of CO2. If that's coming from air, we went to the market and we asked all the direct air capture companies in the world, can you give me a facility that gets 14,000 tons per day of CO2 out of the air? They said, no, our biggest unit today is 1 ton per day. So imagine this difference, yeah? And they said in 5 years, we'll be at 10 tons. So I have to wait 25 years before I can even buy a facility to get 14,000 tons per day of CO2 for a reasonable size methanol plant. You could do it from a power plant. One power plant puts out about 8,000 to 9,000 tons. A good 1 gigawatt facility will put about 8,000 to 9,000 tons of CO2 out per day. So if you get it from a power plant, it's doable. But you got to take out all the impurities, no oxygen, no nitrogen, no NOx, no sulfur. You need food-grade CO2, as we say. And that's not cheap, okay? Food-grade CO2 today is $150 a ton. So this is the challenge we have with this process, is we know the chemistry works, yeah, but actually building a facility at scale is challenging. And this is a techno-economic model which says, okay, if we have energy at a reasonable price, $20 a megawatt hour, we can make hydrogen anywhere from $1.50 to $2.50 per kilogram. And then based on the CO2 sourcing, we can get a specific methanol price. And the best case scenarios you can come to are around $350 per ton of methanol. And gray methanol today from hydrocarbons, it's about $200 a ton, $200 to $250. So the best price here is about $350. But in reality, The best case is $350. The real case is more like $700 to $800 a ton. So it's about, the price of methanol is going to be about 2 to 3 times that we get from hydrocarbons. Now you could take this methanol and you can use it in vehicles, as we've talked about already, or you can convert it to gasoline. And that's I'll take 1 more minute to talk about this process. This process is also well known. You take methanol, you convert it to dimethyl ether, and then dimethyl ether undergoes a process to be converted to hydrocarbons. So the first process uses a catalyst, alumina-based catalyst. The second reactor, DME to gasoline, is a zeolite-based catalyst. This process existed in the mid-80s already in New Zealand. They take coal, they made methanol, and from methanol they made gasoline. And now we want to redo this process, but using green methanol. So you take crude methanol, you go to the DME reactor, which has the alumina, you take the DME into an MTG reactor, which has the zeolite, and then you make hydrocarbons, which then are separated out to make gasoline fractions. And finally, I just show the major challenge with this process is you go from methanol to DME, but DME goes to alkenes or olefins, and then you have aromatics process where this is aromatized, and also you get some alkanes. But the major fraction you get is aromatics, things like toluene, benzene, xylenes, and a lot of durine. This molecule, and this molecule, durine, has to be further hydrogenated to make alkanes. And overall, you can make a very high quality gasoline, but you can see here we need even more hydrogen because we've got to take all these aromatics, saturate them to make hydrocarbons again. And in the end, okay, this process adds more cost. We have calculated for $350 per ton methanol, your gasoline will cost about $2 a liter. So you said in Europe, in US, you like gallons. So it's about $8 a gallon, yeah? A bit less than $8 a gallon or $2 a liter. In the best case scenario. In the worst case scenario, it's going to cost about 2 to 3 times that because the methanol costs will be higher. Okay, so just in summary, okay, net carbon-free fuels, they're possible to produce. We can make them drop-in friendly for existing engines. We can use all our knowledge of combustion chemistry of hydrocarbons to make sure that engines still operate at their best conditions. But it's not always a case that you get lower carbon footprint. You have to choose the right processes, and you have to build things accordingly. So, okay, I'll stop there. We'll go for lunch.
Thanks, Mani. Excellent. Okay, one question.
Thank you, Professor Mani, for a very practical presentation. I had a question on the hydrogen plants. You mentioned that water shouldn't be a problem because it's not, the amount of water isn't very big. I had a question regarding the land area. Do you require like a big land area to create a hydrogen plant? Because we did a similar exercise a while ago on direct air capture plants, and we had, I think, very similar concerns towards land area and water. So could you expand on the requirements for water and land area?
Well, the land area is the renewable energy system. So the electrolyzer facility, 200 electrolyzers or 110 electrolyzers, you know, it's your standard, it would be a standard industrial facility, maybe 2 square kilometers of electrolyzers and Haber-Bosch plant. But of course, the big part is the renewable energy. It takes a huge amount of area. A 2.2 gigawatt wind farm, yeah, and sorry, solar farm, 1.2 gigawatt wind farm. These are very large areas. So in the desert, okay, we have the area, yeah, but in other parts of the world, it's not necessarily the case, yeah. So most of the energy area is required for renewable energy production. And I think the same is true for direct air capture, because for direct air capture to be viable, you need the electricity to come from renewables. So most of the footprint is going to come from the renewable energy facility. Again, so I think it's not like hydrogen production is not increasing significantly compared to the renewable energy that we require for the world. You know, we might add more for hydrogen capacity. The hydrogen production part is not the big one. There was a study in Australia done by Siemens, and I'll try to find that talk and maybe share it with everybody. That talked about if you want to do this whole greenifying of the entire economy, what would it take in terms of power requirements? So first, in Australia, of course, you have renewable energy, you do direct electrification of households, of vehicles, of industry. But of course, there's many places you cannot directly electrify. So you need hydrogen. So they calculated for direct electrification, so fossil fuels, I think they're currently something around 150 gigawatts of electricity capacity. To go for direct electrification, it would be about 250 gigawatts, because you have to build overcapacity if you're building renewable energy projects and getting rid of fossil fuels. And then if you want to do hydrogen, it's about 4 times higher. It's about 800 gigawatts. So imagine that. We're going from a country that has currently 150 gigawatts installed capacity to 800 gigawatts to get to net zero. And his argument with this is a massive investment. Is it really going to happen? And that's only in Australia. Imagine the whole world. If you want to go to net zero, we have to basically build renewable energy systems that are 5 to 7 times more than what we have today from fossil fuels. And it's a huge challenge.
Thank you.
Okay, so will you be coming to the poster session tonight?
Yeah, sure.
Okay, so if you have more questions, you will have a chance to talk to Professor Mani at the poster session tonight, starting from 6 p.m.
He asked me in front of everybody. I couldn't say no.
Yeah, exactly.
Yeah.
Strategy. Thanks, Mani.